In this video, I want to do a short introduction for systems of linear equations in 3 variables. But before we get started, let's first consider for a moment a system of linear equations in just 2 variables, which of course means it can be graphed on a coordinate plane in 2 dimensions with an x-axis and a y-axis. For example, let's look at a first line in red, 3x minus y equals 2, and a second line in blue, x minus 2y equals negative 6. These 2 lines intersect at the point 2, 4. Of course, this ordered pair is the solution to the system because it not only is the point of intersection, but it's also the only point that satisfies both equations simultaneously. So how does a system in 3 dimensions compare to this type of system in only 2 dimensions? Well, first of all, we're going to have to add an additional axis to our coordinate plane to create a coordinate system in 3 dimensions. We'll do this by laying our xy coordinate plane flat and then by bringing in a z-axis that will run from top to bottom. So take a look at this and orient yourself a little. Remember though, we're trying to render a 3-dimensional object in only 2 dimensions, so you'll need to use your imagination a little. Adding an extra dimension makes these problems a bit more interesting, especially than like the linear systems in only 2 variables. It's also much more practical when dealing with real-world applications, such as the Global Positioning System, or GPS, which gives 3 coordinates, one for latitude, one for longitude, and one for elevation, which can be used to find any point on Earth. While points in 2 dimensions use ordered pairs, points in 3 dimensions use ordered triplets. Let's try to plot the ordered triplet 1, 2, 3 in this 3-dimensional system. Well, using a 2-dimensional surface to visualize a point in 3 dimensions can be a little tricky, but we can use some extra lines to make our eyes see things correctly. We'll start by drawing a rectangular prism in our coordinate system. From the origin, we'll move 1 unit down the x-axis, 2 units down the y-axis, and 3 units up the z-axis. And again, this motion was because our ordered triplet was 1, 2, 3, x, y, z. The prism can help guide our eyes so we're looking at this properly. And here is where the point will be in 3 dimensions. By taking away the rectangular prism, we do lose a lot of the effect. Another device we often use to help guide our eyes to a point in a 3-dimensional system is by drawing a line from the origin straight to the point and then creating a right triangle with the horizontal leg in the xy plane and the vertical leg parallel to the z-axis. We actually use this to help us calculate the absolute value of a point in space. Of course, that's the distance from the origin. You can see that plotting points in 3 dimensions, like on a piece of paper, would be a bit of a struggle and perhaps not all that helpful. But this does give you an idea of where we're headed. Recall that when you graph a linear equation in 2 dimensions, you get a straight line, just like we saw at the beginning of the video. However, in 3-dimensional space, the graph of a linear equation will actually be a plane. And you have to be careful of the classification linear. It doesn't mean that it's always going to generate a line when graphed. It just means the degree of the equation is 1. Because a plane is defined by 3 points, we can graph linear equations in 3 dimensions by finding the 3 intercepts, one along the x-axis, one along the y-axis, and of course one along the z-axis. For our example, let's go ahead and use the linear equation 6x plus 3y plus 2z equals 6. We can determine each intercept by substituting zeros and solving for each variable independently. For our x-intercept, we'll substitute 0 for y and z, and we see that 6x equals 6, so x will equal 1. We can write our intercept as an ordered triplet, 1, 0, 0. Similarly, we can do that with both our y and z intercepts. we'll see that y will equal 2, so our ordered triplet will be 0, 2, 0, and z will equal 3, so that ordered triplet will be 0, 0, 3. Plotting each of these points in our three-dimensional system looks like this. We can draw helpful lines between each of these points to help orient ourselves, and then the plane generated by this linear equation in three variables will look like this. I went on the GeoGebra website and got 4 different views for this graph, so let's go ahead and take a moment to look at each one of them. At this point, you can probably guess that solving a system in 3 dimensions using a graph can be pretty difficult because most of our 3-dimensional representations happen on a 2-dimensional plane, like a piece of paper or on a computer screen. It is much easier to tackle these types of problems algebraically by using substitution and elimination. Much like a linear system in 2 dimensions, the relationships between 3 planes and a 3-dimensional coordinate system are pretty straightforward. Once again, there are the 3 classifications that we'll use: inconsistent, consistent, and dependent. Here you can see 3 different examples of a system that has no solution. In the example on the left, all 3 planes are parallel and have no points of intersection. In the example in the middle, 2 planes are parallel, and 1 plane cuts the 2 parallel planes, but all 3 planes have no points in common. In the example on the right, the planes are oriented in such a way where each pair of planes intersects at a line, but all 3 planes together share no common points. An inconsistent system has no solution because the planes in the system have no points in common. A consistent system has 3 planes that all intersect at a point. This means the system will have a single solution, and that is the point of intersection. A dependent system has 3 planes that all intersect at a line. This means the system will have an infinite number of solutions. Specifically, every point on the line of intersection will be a solution to the system. So that wraps up our quick introduction of systems of equations with 3 variables and 3 equations. So the big ideas you need to take away from this are, well, number 1, while in 2 dimensions, linear equations generate lines, and in 3 dimensions, linear equations generate planes. The second one, as with 2 dimensions, there are still 3 classifications of systems: consistent, inconsistent, and dependent. And finally, it's difficult to graph 3-dimensional systems on paper, so to solve the systems, we'll use algebraic approaches that include substitution and elimination. Well, I hope you found this video helpful, and be sure to subscribe to my channel for more upcoming math videos.